Hi everyone, thanks for coming. My name is Sajjan, and so here's a quick outline of the lecture for today. So I want to discuss some administrative stuff with you, just basic general stuff, and then we're gonna see the motivation for this conjecture. So this course is about this conjecture called KRW conjecture, and we'll see why this conjecture is important, what implications does it have, and then we'll see like this conjecture talks about this very specific model of computation called circuits. uh, so we'll talk about circuits, and then I'll tell you how this motivation is connected to this model of computation, and then we'll talk about the conjecture and how it implies the desired result. Okay, so let's jump right in. So some administrative stuff. So we're gonna have like 3 homeworks and 1 project, and based on, so I'll wait until Wednesday to see how many people like uh, are signing up for crediting this course, and based on that I'll like discuss with Shahar and decide on a project. Currently I'm thinking maybe scribing or giving presentations, but nothing's decided. So I'll also run a poll with you guys to see what you prefer. So there's a course mailing list. So there are some people who are not from UCSD. There are people from SFU and from other places. So for general announcements, like I had one last week about canceling Wednesday's class and things like that, I'm going to use this mailing list. So if you haven't signed up, please do sign up. And then there's a Piazza core page. So all the course related, like grading related stuff, we're going to discuss there. So if you are from UCSD and you're crediting this course, please do sign up. Currently there's a, yeah, so officers, I am thinking tentatively 11 to 1 p.m. I'm running a poll on Piazza on what available slots are there. So if you folks can vote, that would be great. Again, I'll decide this by end of this Wednesday. So currently it's 11 to 1 p.m. Friday PST. And lecture hours is like Monday and Wednesday, 11 to 12:20. Yeah, I'm also going to post some relevant research papers on the website. So these are going to be the research papers that would motivate and guide the course. So there's a lecture plan already, and it's based on some of these research papers and some ongoing work. So this, as I was telling you, this course is about KRW conjecture, and this section is all about why should we care about this conjecture? What is this motivation? So it basically is a conjecture that would help us understand whether it's about nature of efficient parallel computation. So what do I mean by that? Um, so here is an interesting thing, like an interesting fact. So if you think about most problems in linear algebra, it can be done in efficiently in parallel. So for some theoretical definition of parallel, which correlates to like how parallel algorithms are implemented in practice. But there are certain problems like Gaussian elimination, which are sort of an outlier. What do I mean by that? There are no really good parallel algorithms for these problems. And if you remember Gaussian elimination from your undergraduate algorithms course, you intuitively know that it's kind of a sequential algorithm. So you go through, so you're given a matrix and you have like a bunch of rows. So you go through each one of them one by one, you choose a pivot and do some kind of normalization, and then you compute the rank, right? So it sort of feels like an inherently sequential algorithm and intuitive, if you have seen that. Otherwise, believe me on this. And there are also theoretical reasons to believe that a problem like Gaussian elimination doesn't have efficient parallel algorithms. In fact, it's not for lack of trying. There are deeper reasons. Okay, there are a couple of more people. Okay. So, but as you know, there's like an order n cube algorithm, right? It's inherently very sequential. So the question, so this P versus NC1 question is it's just like trying to understand this phenomenon. So it's us like other problems which can be efficiently solved by sequential algorithms, but which do not have any efficient parallel algorithms. Okay, there are more people. Okay. Um, so a couple of more people have joined. So if you have any issues, please uh, unmute yourself and ask questions or raise comments. So, so it's telling you this P versus NC1 problem is about like uh, efficient sequential computation versus efficient parallel computation, and efficient sequential computation is represented by this well-known class P of polynomial time solvable problems. Okay, and efficient parallel algorithms, they're going to be like modeled as circuits. So this is a different computation model. So we'll get to what circuits are. So I'll start with an example and then we'll formalize this notion. Okay. Suppose you're given a Boolean function. For example, here we have the 2-bit parity function. So it checks if there are this like an odd number of ones in your input. So it's also known as yeah. So here what I've drawn here is a truth table of this function. So it's a 2-bit functions on all possible inputs. We are f- uh, we have written the value of the function on all possible inputs, right? So this is the parity function, and here is a circuit computing this function. Okay, so what does this function do? It computes this. So the inputs are the variables or its negations, they're called literals. So that we have two inputs, I mean four literals. So you have inputs x1 and x2 and literals, and their complements x1 bar and x2 bar. And what we are doing is like first we are computing an AND, logical AND of x1 and x2 bar here, and then we are similarly computing a logical AND of x1 bar x2 and then taking a logical OR operation, and whatever is the output at this point is the value of the function. So I claim that in fact, right, if you using very basic Boolean algebra, you can write this as indeed x1 and x2 bar plus x1 bar x2. Okay, so it is an example of a Boolean circuit computing a Boolean function. Okay, but what is this formally? So we have like a bunch of nodes which we call the input, and then there are some nodes which do the computation. These internal nodes are so for the rest of the course we can assume that they're like logical and or gates, and any negation happens at the input level or at the leaf level. Okay, and there's this one designated node, it's called the output, and it computes the Boolean function that we want. Okay, so let's define circuits formally. So I've just copied the same circuit over here. So circuit is like a directed acyclic graph. You can think of like so here every edge in this graph is like directed towards the root and away from the inputs, and at the bottom of the circuits we have a bunch of nodes which are called leaf gates, and there are other nodes are called internal gates, they do the computation. So whenever we introduce a complexity like a computing model, the interesting question to okay, so someone else is here. uh, Interesting questions to ask about a computation model are what kind of resources are there, like what kind of resources are there that this model uses for computation, so that we can place meaningful bounds on these resources and ask like uh, complexity theoretic questions. So for circuits, so one important parameter is called size. So it's basically the number of gates in the circuit. So in some definitions, the gates are only the internal gates. So that those are the gates which does the computation. In some definitions, it also includes leaf gates. So for us, it's not super important how this is defined, but it's roughly the number of internal nodes. So the other measure that is going to be important for us is called depth. So this measure is like the length of the longest path from the output of the circuit to one of its input. So if you have not seen this earlier, it might seem like an arbitrary definition, but it has like, so this is an intuitive definition if you're trying to understand parallel computation. So why is that? Okay, so there's some other small, so before telling you the intuition behind depth, let me tell you some other parameters. So the other, another thing is, it's called fan-in. So basically for every gate, so for example, the gate here, how many other gates are feeding into it, this is called the fan-in. So basically, uh, in in the rest of this course, we'll assume that fan-in of every internal gate is exactly 2. Okay. Another parameter that is interesting is called fan-out. So you have a gate, so it does some kind of computation. So how many other gates does it feed to? So in this example, fan-out, so this is called fan-out. And in this example, fan-out of every gate is exactly 1. So we'll assume that, sorry. Um, yeah. So we'll assume that fan-in is 2, fan-out is 1. Okay, I did not write that. Oh, there's some other thing. So yeah, now I want to tell you the intuition behind why depth is sort of equal to parallel time. So there's some animation which is supposed to come later. Apologies for that. But um, okay, so so we'll make this assumption that every internal node represents some computation that can be done in unit time. So it's some kind, so every internal node, we think of it as a separate parallel processor, and every computation that it does, we'll assume that it takes unit time. So this is it's a natural assumption to make, because we are restricting our internal gates to be very simple logical operations, so you can assume that they can be done in like unit time. Okay, so by the definition, so here is a simple circuit. Okay, so these things should not be there. Sorry. Yes. So here is the simplest possible circuit. It's just one input node, and that itself is the output node as well. So it looks at an n-bit input and it just outputs one of the bits. So it's like the simplest Boolean function that you can think of, and it's also a very simple circuit. And if you think about a definition of depth, it's like the length of the longest path in terms of number of edges from root to the leaf. But here the root and the leaf are the same, so the depth is 0. Okay, so if you think of depth as an inductive definition, depth of every input is like, it's for free, it's a 0. And now let's add one more level of computation. So yeah, so then we take and of this xi with xj, and what happens to depth? So this circuit just computes the OR of xi and xj, and by definition depth of this circuit is 1. Okay, because this like, so either to go to xi or to go to xj, you need to traverse one edge, so depth is 1. So now let's add one more layer of computation, and this time we are taking an AND of this pre-computed value with xk. So now if you think about depth, there are like, on this side of the circuit, uh, the length of the longest path is just 1, but on this side, the length of the longest path is 2, right? And by definition, depth is the maximum of these two, so the depth of this circuit is 2. Okay, so yeah, yes. So now let's take this to a very general example. So suppose you have a circuit, let's say its output gate is and it's taking the AND of another circuit C1 and a sub circuit C2. Okay, so C1 is a, let's say, depth denotes depth of C1 by depth of C1, depth of C2 by depth of C2. And by definition, so by this inductive definition of depth, so depth of this entire circuit at the root is the maximum of depth of C1 plus depth of C2. So sorry, maximum of these two things plus this. So on either side you have to take this edge plus 1. So if you think about like our motivation from parallel computation, so you think about this sub-circuit has done some computation in parallel time exactly this much. Let's call this like, I don't know, 10 or something, and this took 5 steps. So after 5 time steps, this circuit would have produced an output, right? But to compute the AND, I mean, if this circuit produces something like 1, then we don't know what's the value of this AND is going to be. But if it did produce 0, then we know AND of 0 with anything else is 0. But in case this sub-circuit did the computation and produced a value 1, then after 5 time steps, we cannot output the value, right? So in that case, we have to wait for C2 to finish computation. And C2 takes 10 steps. So after 10 steps, we have both the output of C1 and output of C2, and at this point you can just compute the top gate, and it takes another 1 unit of time. So the depth is going to be the max of 5 comma 10 plus 1. So in this model where you assume that every node is a separate parallel processor of itself, and each computation done at a node takes unit time, depth represents parallel time, right? So that's that. Are there any questions at this point about the circuit model or this definition of depth? Okay. If not, let me move on. So I want to like tell you one more model of circuits. It's called formulas. So these are circuits where the underlying graph is a tree. So what do I mean by that? So it intuitively corresponds to a model where you cannot reuse computation. If that doesn't make sense to you, it will make sense in a minute. So let me give you an example of a circuit which is not a formula. So if you think about this circuit here, so it computes some Boolean function on 4 bits on x1, x2, x3, and x4. So if you look at this sub computation, it computes the AND of x1 and x2, right? And then it reuses this computation to compute the AND of this thing with x3 and to compute the AND of this thing with x4. And if you look at the graph, underlying graph, you can see that at the end of the day, all the internal nodes finally reach the root. So because of that, there is like, if you look at the undirected version of this graph, there is a cycle. So there is some cycle like this. Okay. So this is what is an example of a circuit which is not a formula. So but how do we make this a formula? So in a formula, like you cannot and any internal gate has fan out exactly 1. So an internal gate represents some sort of subcomputation, and the output of that subcomputation can be only given to one other gate. So if you remember, fan out is the number of other gates a gate feeds into. So a formula is equivalently a circuit where fan out is 1. And so I'm transforming the circuit from the example which was not a formula into a formula. So how do we do that? So we remember that this AND gate actually needed this x1, x2 and to be fed into it. So we take that away, and we add another duplicate copy of the exact same circuit, exact same copy of that sub-circuit, and feed it in independently. So in this graph, if you look at it, every gate feeds into exactly one other gate. There are no cycles in the underlying graph, underlying undirected graph, and the underlying undirected graph is a tree. So there's this well-known theorem from graph theory which says that you can balance every sort of unbalanced tree into a balanced tree. So if you don't know this fact, maybe we can discuss this in office hours, or maybe I'll give this as an homework. And using this fact, you can prove that for every formula, you can, without loss of generality, assume that depth is comparable to logarithm of the size. So in a circuit, it could be very skewed. in a formula also it could be very skewed. There could be like maybe on the right mode side you have a very lengthy path, and the left mode side you have like really small paths. So in general, formulas and circuits can be very unbalanced. So but in formulas you can always rebalance them, because the underlying structure is a tree, and you can assume that these two complexity measures, size and depth, are in fact asymptotically related. So if you want to understand size of formulas, it's enough to understand their depth. Yeah. Okay, so some so here's one more observation that I want to tell you. So in general, like converting a circuit to a formula can be very expensive. So like roughly, if you have a depth these circuits, you have to, so the last slide we saw this example where we had a circuit which was not a formula, to make it a formula, so we kind of replaced every gate that fed into multiple gates with duplicate copies. So in general, if you analyze this procedure, you'd get that the size of the resulting formula is something like exponential in depth times the original size. So if you have a size S depth D circuits, so that means that the circuit has S internal nodes, and the longest path from root to any input is D, at most D. Then you can convert into a formula where the underlying graph is a tree, where the size is going to blow up. It's going to be 2 to the D times S. Okay. So, but for certain parameters, it's really good. So if you have a polynomial size circuit and which has logarithmic depth, by this rough calculation, you can see that 2 to the D, 2 to the log is log n is like 2 to the C log n is n to the C, so that's polynomial. And so S is polynomial, 2 to the D is polynomial, so polynomial into polynomial is again a polynomial. So you get that like polynomial size logarithmic depth circuits are equivalent to polynomial size formulas. Okay. So, but why did we talk about circuits? We wanted to talk about this this class of efficiently solvable efficient problems which are efficiently solvable in parallel, right? So this is going to be, so in the circuit model, this is going to be the class NC1 of polynomial size formulas, and it actually relates to a practical model of parallel computation called the Crew-Pram model. It's from the 90s. But in terms of a circuit class, what is this definition? So it's, so in the Crew-Pram model, you want to say that something is efficiently computable in parallel if there are polynomially many processes. And I kind of alluded, like try to convince you that in circuits, the processors kind of correspond to the internal nodes. They do computation, right? So this translates to the size of the underlying circuit being polynomial. Okay. And the other thing we wanted is like, so we wanted the parallel computation to be very fast. So what is very fast? So so the definition of very fast for this model is logarithmic in input size. So something like C log n time. And what's the associated measure in circuits? So it kind of convince you that depth of a circuit sort of roughly corresponds to the uh, parallel time in computation. So this is equivalent to saying that we want our underlying circuit to have logarithmic depth. So you're trying to model this notion of efficiency of parallel computation, where we say that there are polynomially many processes and the total computation takes only logarithmic time in parallel. If you run, so think of the circuit as sort of layers, from transforming input to another layer and so on and so forth, and reaches the output node. So every layer it does computation in parallel, and then you feed into the next layer. So the depth is the amount of parallel time it takes. So NC1, so this class NC1 is this class of circuits where the underlying circuit has polynomial size and logarithmic depth. But if you remember from the couple of like I think 2 slides ago, we said that but if the underlying circuit is a formula, then depth is in fact the logarithm of size, so that requirement is not needed. So if you think about size being polynomial, and then what's the equivalent depth using this formula, it's just logarithmic. So any polynomial size formula can be rebalanced to make to make something which is polynomially sized and logarithmic depth. So whenever we think of parallel computation, now we can just think of polynomial size formulas, and without loss of generality we can assume that they have logarithmic depth. So now let's go back to this question, which is the motivation for this conjecture, this P versus NC1 question. So what is this question in terms of this circuit model? So we want to find a function which is efficiently computable in efficiently computable sequentially. So we want some function which is in P, in the class P of polynomial time algorithms. So there are candidates like Gaussian elimination, finding perfect matching in a graph, etc. So they have to be computed in polynomial time. And okay, so I did not exactly define De Morgan formula, but De Morgan formulas are the kind of formulas we have discussed so far. So their internal gates are and or gates, and every their inputs are either the variable or its complement. Okay, and fan in is 2, fan out is 1. So we want to say that we said that this class of parallel algorithms is equivalent to polynomial size formulas. So we want to say that this function doesn't have efficient parallel algorithms. So equivalently, we want to say that there is no formula computing it which has polynomial size. So any formula computing this function should have super polynomial size. But if you remember, in formula, size is approximately equal to logarithm of the depth. So it's essentially trying to say that any function f, so there's this function, candidate function, any formula that computes it must have super logarithmic depth, okay, or any circuit, just for this class. So this is our target. So we want to come up with a function in P so that every formula computing it must have super logarithmic depth or super polynomial size. But what's the state of the art? It's not really good. So the best formula lower bound is like a celebrated result from the 90s due to Johann Hastad, and it has been recently improved by Avishai et al. So it gives, so what kind of lower bound does it give? So remember that our target is to prove a super polynomial lower bound. So this gives a cubic lower bound. So if you think about it, every formula should have at least size n, because if your function depends on all the inputs, you have to look at all the inputs, and that requires n gates, right? So that's sort of the trivial lower bound. So this lower bound is highly non-trivial. It's saying that, okay, there is some function, in fact, for the function for which this lower bound is proved is NP. It's a simple function. It's and this function has, any formula computing this function requires almost cubic size. Okay, and if you think about depth is the logarithm of the size. So this is saying that any formula computing this function must have 3 log n depth. Okay, but remember that this is very far from our intended goal of separating P from NC1, because we need to prove a super logarithmic depth lower bound or a super polynomial, equivalently a super polynomial size lower bound. Okay, so but you might ask, is why is there such a gap? So there are these meta mathematical barriers which say that certain kind of proofs cannot establish this result unless some widely believed cryptographic and pseudorandom assumptions are false. So most complexity theorists believe that these assumptions are indeed true. So hence, like, the kind of techniques that yielded a lot of results in the 90s and even until now, like, a lot of these techniques cannot be used to prove a super logarithmic depth lower bound. So I don't want to get into the details of this, because then I'll have to talk about pseudo randomness and stuff like that. But it's a really interesting result. It's a, yeah. So there are barriers. So we need, so our goal is to, like, okay, so if you want to really understand this problem and make some progress, you need techniques, proof techniques that are beyond these barriers. Okay, so here's where KRW conjecture comes into play. So KRW conjecture is like one of, if not like the only one. Okay, I don't want to make such a general statement, but it's one of the uh, promising approaches which is not known to be limited by any of these barriers. So the known barriers like natural proofs do not apply to this proving P versus NC1 using KRW conjecture. So for this reason, it's very hopeful. Like maybe so. I should warn you at this point that P versus NC1 is considered to be like a very hard problem in complexity. So making progress on it's going to be very difficult. But there are no formal barriers that stop us from using KRW conjecture to solve this problem. Okay. So let me get into this. So if you are convinced that P versus NC1 is an important problem, and if you believe me that there are mathematical barriers on what kind of proofs can resolve this problem, then KRW conjecture is one of them. So let's get into the details of the KRW conjecture. So KRW conjecture was a conjecture made by Mauricio Kashmir, Ranras, and Avi Vigderson in the 90s. So the generality and the simplicity of this conjecture is that to they say that to understand depth lower bounds in a circuit or how computation happens in formulas, it's enough to study a very natural and well studied uh, composition of Boolean function called the block composition. So this composition operation actually as is used in some other areas like lifting, etc. So it's a very useful notion. So they say that if you can understand depth complexity of this very basic operation of on Boolean functions, then indeed you can resolve the P versus NC1 problem. So let me tell you this, what is this composition? So we'll see this formally and we'll see with the diagram what this is intuitively about. So you're given two Boolean functions. So the first one is, let's call it f. It's a function on m bits. And let me denote the variables of f by z1 to zm. So it's a function which takes m Boolean bits and produces 1 bit of output. And we're given another Boolean function, let's call it g. It's on n bits. M could be n, m could be much smaller or larger compared to n. I don't know. But so it's defined on n bits. It takes n bits of input and produces 1 bit of output. Let's say it's on variables y1 to ym. So then the block composition of f compose g is a Boolean function on m times n bits. So it takes m n bit inputs and it produces 1 bit of output. Okay. So how do we so how is this defined? So you think of the inputs as like m blocks of length n. So x11 to x1n is one input block of length n. So let me call this y1, and the next n bits are going to be y2, and the next yeah, sorry. So no, what I want to say is that I want to think of this as like inputs to g. So these are like y1 to yn that feed into c. So there's a typo here. This should be n. So g takes n inputs. And so this is going to be some other bunch of y1 to yn that goes into g. So how is this function defined? So you define this function as f on z1 to zm, where zi is g applied to the ith block of n bits. So xi1 to xin. Okay. So you first so you divide the input is mn bits long. You divide the input into n length chunks. So there are going to be m such chunks, and on each of these chunks you apply g. So you apply g here and get 1 bit. So this is z1. You apply g here, you get zm. So in this process you will get z1 to zm, and f takes m bits. So you apply f on this and then you get 0 1 value. So this is f compose g on mn bits. So this is the definition. So if this definition was too technical, let me illustrate it with a diagram. I've just copied the definition, formal definition here. But now I want to think of the inputs to f compose g as a Boolean matrix. So this matrix has m rows and n columns. So if you think about the number of bits in this matrix is exactly mn, right? So, and if you recall, f compose g is a function on mn bits. It takes mn bits and it produces one bit of output. So the definition of f compose g can be thought of as follows. So you first so you first apply g to um, so you first apply g to each of these rows. So there are m rows, and g is a function on n bits, so it can take one row and produce one bit of output. So you apply g on every single row, so then you get this intermediate input, which you which is like how many bits are going to be there. They're going to be m bits. They're going to be exactly as many bits as there are rows. So you take these m bits and then you feed this into f, so then you get a 0 or 1 value based on what f, right? A1 is 0 and this one is 1, and alternative like way to look at this definition. So this definition is going to be very crucial for the rest of the course. So this would be a good time to pause and ask questions if there are any questions about this definitions or anything before. Um, Also, as I was saying, like with the kind of interface I have, I really can't see chats here. So if you have any questions, please unmute yourself and ask questions. Okay. So if this is clear to everyone, let me tell you like so let me tell you why this definition what is the KRW conjecture. So once we now have this definition, I can tell you what is the conjecture. So conjecture is about this block composition. So recall that block composition is this operation which takes an m-bit function and composes with an n-bit function to get a function on mn bits. Okay, someone else is here. Okay, so you can think of this. So you can think of computing this f compose g using circuits. Okay, so here is a circuit that computes this composition. So the formula, so I first take a circuit or a formula that computes f. So and what form, and this is about the depth of circuits. I take the best circuit that computes f in terms of depth. So a, a given Boolean function can be computed by many different circuits, right? Some of them might be optimal in the sense that they will have minimum possible depth, and some of them might not be not optimal. So among the circuits that compute a function, I take the best circuit in terms of depth. So depth is this length of the longest path from root to a leaf. So I just take the circuit with this minimum depth. So CF, I'll assume that it's a circuit that computes f with minimum possible depth, and I'll denote depth of the circuit by d of f. So earlier we called it depth of f. So from now on, I'm going to drop depth and just call it d of f. And whenever we denote size of f, we'll just call it s of f. So how do we compute this composition? So remember that there are these. So C of g is equivalently is a circuit that computes g, the Boolean function g, and it's also the best depth possible. So remember that f compose g takes mn bits of inputs, and we divide this mn bits into n bit chunks, right? So basically x1 is the first row here, x2 is the second row, xm is the last row. Yeah, so you take this input, so this is, and then feed into C of g. So by the way I have drawn this circuit, it sort of looks like the circuit has only n leaf gates, but it could have like many more than n leaf gates. So whenever it reads a particular input, I'll feed that into that particular input gate. So in general, like the number of leaves of this circuit or formula could be much more than n, but every leaf is labeled by one of these inputs. Okay, so you give this input to this circuit CG, so it computes G on X1. Oh, sorry. Okay, I went too far. Yeah, so it computes G on this first one, X1, the row X1, and it computes this values. And then you compute G on X2 using CG, another copy of the circuit, so on and so forth. And then you compute all these values. So these values are the values here. And then these are the inputs to the function f. So you can feed them into a circuit that computes f. So that's exactly what I've done here. And then you get that you apply this circuit, and this gives you the value of f compose g. So this is indeed a circuit that computes f compose g. This need not be the best circuit that computes f compose g, but it is a circuit that computes f compose g, and given the best circuits for f and g individually. Okay, so is this clear to everyone? So yeah, so what does the KRW conjecture say? So it says that, okay, so remember this circuit that computes f compose g using the best circuits for CF, best circuit for f, and best circuit for g. It's it says that, so it's let's first analyze the depth of this new circuit that computes f of compose g. So what's the depth of this circuit? So it's the length of the longest path from root to one of its leaves. So the leaves of this entire circuit is these values here. So these are the leaves, right? These are the leaves, and this is the output gate. So what is the depth? So it's the length, it's the depth of C of f, which is d of f, plus the depth of C of g, right? It's these two lengths added together. So it's clear that if you want to compute f compose g, then you can compute it in depth, at most f, depth of f plus depth of g. This may not be the optimal way to compute it, but this is a way to compute it. So maybe the best possible depth is much better than this, but it's not more than this, because here is one circuit that computes f compose g with this depth. So the KRW conjecture says that if f and g are non-constant Boolean functions, this sort of naive formula, which uses the best formula for f and best formula for g, is indeed an optimal formula for computing f compose g. So to compute f compose g, we don't have to compute it this way. Maybe there's some other crazy way to do it. So this is just one way, but the conjecture says that, okay, approximately, so I'm not going to define this approximately right now. So I'm going to leave it vague for a while, because there are many like competing definitions of approximately that is good enough to give the final result that we care about. So KRW conjecture implies P not equal to NC1, and to get that result, there are many different versions of this approximate equality that you can plug in and still get the result. So, but forget those technical details. So what this conjecture is saying, that this naive way of composing the optimal formulas for f and g to get a formula for f compose g is also the optimal way to compute f compose g. Okay, so some subtlety here. So the this circuit is not the only way to compute F compose G, so you should realize that. So it's just mimicking the definition and building a circuit based on that definition, but there are other ways you can build this circuit. Okay, so this is a very strong statement, right? This is about like all possible functions f and g which are not constant. So there's a very simple reason to rule out constant functions, because if you allow a constant function, the conjecture is not true. Say the function f is a constant one function, so only two constant functions in Boolean functions, right? It's the constant one function which always, no matter what the input is, output one, and the constant zero function which always outputs zero. Let's say f is the constant one function. Then to compute f compose g, you don't really have to compute an input to f, because no matter what the input is going to be for f, it's going to say 1. So you can just take the trivial circuit which just always outputs 1, and that's a circuit that computes f compose g, and it has no relation to depth of g, right? So f and g has to be non-constant for this conjecture to make sense. But KRW posited that this conjecture is indeed true for any non-constant f and g. So what does the conjecture give? If this conjecture is true, we get an explicit function. So I've put explicit in red because it has a certain meaning in complexity theory. So it means that it's not some kind of cooked up function. It's not some kind of function which says like, okay, there exists some function, but it's something you can construct. So given the input value, you can sort of construct the definition of the function, or it's like easy to describe function. So I'm not going to formally define what this means. So there's some function, explicit function, which can be computed in polynomial time, but it doesn't have logarithmic depth circuits. So basically this function is not an NC1, and this is what we wanted to prove, right? So there's some efficiently solvable problem which is which is inherently sequential in the sense that it doesn't have efficient parallel algorithms. Okay, so if you prove this very fundamental fact about uh, depth of a certain composition, this block composition of Boolean functions, then you can prove that P is indeed different from NC1. Okay, so we'll see how that is, why that is the case. So for that, I'll switch to good notes, and then I felt like this part it's maybe easier to describe with notes, handwritten notes. But let me know if you think, if you don't find that very effective. So for the future lectures, I'm thinking a mix of both uh, presentations and mostly handwritten notes. Okay, so if you, yep, sorry. So let me go over to good notes. Okay, so just to summarize, what we saw is a KRW conjecture. So let me just rewrite it here. Conjecture, it says that for any f comma g, I'm not going to repeat, but whenever I say this conjecture, it means that f and g are not constant functions. So depth of f compose g is approximately equal to depth of f plus depth of g. So we want to say, okay, so this is going to be the assumption. We're going to assume that this is true. I'm not putting, like, I'll define this approximate equality later, and once we complete this discussion. So I want to use, like, define this vaguely using this approximate equality, and then I want to say that claim this conjecture, KRW conjecture, implies super log formula depth bounds. Okay, so if my handwriting is not clear to anyone, or if you have any issues, please unmute yourself and let me know. I hope everyone can see the notes. Okay, yeah, feel free to interrupt me whenever you have questions. Okay, so how are we going to do about, like, how are we going to prove something like that? So let's try to understand what this conjecture if true means. So it says that, okay, so under this block composition of function, depths is the if you think about the best formula that computes f compose t, its depth has to be depth of f plus depth of g. So if you have like some kind of function, so say sorry say that there is some function h on, let's say, k bits. Sorry. So which has good depth to start with. So it might not have like super logarithmic depth, but maybe it has some kind of good depth to start with, and we'll see what is a definition of good. But then what can we do? So so we have a function h which has, say, depth d of h. So we want to like get to another function which has like larger depth under this KRW conjecture. So what can you do? So one natural thing is like, this conjecture talks about block composition of Boolean functions. So maybe one idea is to just compose h with itself, right? So what happens is that, okay, so let's look at the block composition h composed h. So what's the length of this function? So it takes k inputs of h and feeds it into h itself, right? So this is, so if you think about h composed h is basically like you have x1 which is k bits, so then you apply h on this, you get 1 bit, so on and so forth, and you apply xk which is another k bits. So this, the entire input is k square bits, right? So k times k is k square bits. So you apply k copies of h, then you get intermediate bits z1 to ck, and then you apply h again, and then you get 1 bit. So, right? So, and if KRW conjecture, so I'm not going to write KRW conjecture, but I'm just going to write KRW. So if KRW conjecture is true, then what do we know? We know that depth of h composed h. So I'm going to replace the approximate equality with equality for now, and we'll see that all these definitions of approximate equality, the proof I'm going to describe to get the claim, would give you the claim. So for now, let's assume the best possible thing, that is depth of h plus depth of h. So if you think about it, so we had a function h which had depth d of h, and now we got a function whose depth is twice that of d of h, right? And why stop there? We can, in general, we can, so if KRW, then we can compose h with itself like k times, I don't know, not k times, maybe like let's say n times. So in general, I'll denote this with h, and so it's not the best possible notation. So, or maybe yeah, I think the better notation would be h to the n. So it's like n compositions of h with itself. So under the conjecture, it is depth of. So you can think of like, okay, so how do we like, yeah, so this is one subtle issue. So that the KW conjecture was about composition of two functions. So here we have like more than two functions. So how do we like apply the conjecture? So you actually can group these compositions into two parts. So let's take the example of three composition, h composed with h composed with h. So we saw that h composed with h itself is a Boolean function. So this h composed with h was this Boolean function on k into k square bits, and made 1 bits of output. So you can think of this as a function g. So this is equivalent to d of h composed with g. Pictorially, what is happening is that h composed h would be a function on to the k, which is k cube bits to 0 1, and pictorially what would happen is that you would group your inputs into uh, k square bits this time. And what would you apply? You would apply h composed h. So it's like a picture. If you zoom in, you would get this value, this structure, right? So this is internally, this is like, okay, maybe I should use some other color. So internally, this is like, um, you divide x1 into x11, which is k bits, and x1k, and then you apply h on each of these chunks. You get k bits z1 to zk, then you apply h again. Yeah. So internally, you can think of this as like this thing. So you apply h composed h on these k square bits. So you would get bits z1 to zk again, right? There'll be k bits, and then you can apply h. That's one view. Another view would be to group the other way around, right? You can think of, so I said like, so this is the view where I think of composing h with g, but because this is composition, it's associative, you can also think of it as equivalently as g composed h. So that's a different way to think about this one. So you can think of so g is a function on k square bits. So this was describing h composed g, where g was h composed h. Another way is to think of it as g composed h. So where you would divide your inputs into x1 to xk square, where each of them are k bits in length, and then you would apply h, right? So you would get k square bits of inputs. Let's call it z1 to zk square, and this is the input to g, which is just h composed h. So there are two equivalent ways to think about this, but you get it, right? You just group, like if you have n compositions, you, in general, hn is in our notation, it's h composed hn minus 1, or you can also equivalently think of it as hn minus 1 composed with h. So these competing definitions would make sense once we get into the finer details of the conjecture. So one of them is useful, more useful than the other, but for now, at least understand one of them. So this is a way to like think of many compositions as two compositions at once. So under the conjecture, what happens to h composed h many times? So let's use the first definition, which is just h composed hn minus 1, which is the, so under the conjecture we know that for two functions, this is a one function, this is another function, the depth should be d of h plus d of h n minus 1. And if you expand this recursively, any guesses what's it this is going to be? So if you do this is one more time, it will be d of h plus d of h n minus 2, right? So on and so forth. So this is a simple recursion, and if you work it out, it's very easy to see. It's just n times d of h. So if the conjecture is true, so we can take a function which had like sort of okay depth and get a function which has much higher depth. Okay. So why does this conjecture only imply something like super logarithmic depth bounds? Maybe I can like compose it enough time to get any kind of depth lower bound, right? But there's a catch. So whenever we so in asymptotic analysis, we always, so the the computational resources, be it time or space for Turing machines, or size or depth for circuits, it's always measured with respect to the input size, right? So just I wanted to briefly mention this trade-off. So we saw that if KRW conjecture, the depth of H composed n times is n times depth of H. But what is the size of this, like input size of this function as compared to the input size of H? So remember that we call that H is on k bits, right? So the first time you composed H with itself, it became k square. The second time it became k cube, so on and so forth. So if you compose it n times, it's going to be k to the n sized. So H of n is on, so the input size went from k, so it went from k to k to the n, and the depth went from depth of H to n times depth of H. So at some point, the gain that you get from composing in terms of depth is going to be like overshadowed by the explosion in input size. So there's some kind of natural equilibrium point where your gain in depth is the maximum possible, and beyond that, this conjecture doesn't give you anything more. So is this clear to everyone? Are there questions at this point? It would be a good time to ask. Okay. If not, let me tell you how to get P not equal to NC1 from this conjecture. So basically our idea is going to be compose some good function which has a good depth lower bound many times so that we get a good depth lower bound. So here is some kind of well-known fact from circuit complexity. So I don't know if everyone has background in circuit complexity, so if some of these things are like new to you, and if you have questions, we could like discuss over office hours, or you could just email me and we could like find some time to discuss. So this is well-known fact that there exists some function. So for any input size k, yeah, there exists some Boolean function h on k bits such that the depth complexity of h is, the formula depth complexity of h is something like k over log k. Okay, so you might already ask like, but then this would already solve our problem, right? This function clearly doesn't have logarithmic size formulas because the depth has to be at least or exactly approximately equal to this much. And if you remember, NC1 circuits are circuits where you're only allowed log k depth. So this is a function which is clearly not in log k depth. It's much higher. It's almost as high as possible. Sorry, I think there's someone else here. Yep. So then this should solve the conjecture, right? So here's why it's not true. So remember that we wanted a function h that was in polynomial time, and also it should be an explicit function. So the way this fact is proved, it's done by a counting argument. So this function is neither explicit or nor we know that it's in P. So it could be even undecidable. So this is not a good candidate for getting the actual lower bound, but we're going to do some kind of hack to this function so that we can encode it as part of our input, and that's how we are going to get the lower bound. So we're going to shrink k compared to the final function that we're going to get and do something. Okay, as I'm getting ahead of myself. So, but so this is a well-known fact. This is not necessarily an explicit function, but all it is says is that okay, there is some truth table. So every function. So how are we going to represent function? We're going to represent functions as truth table of that function. So if you remember in the earlier slides, we had this truth table for the 2-bit parity function. So it had 4 rows, right? So the number of possible inputs on 2 bits is exactly 2 to the 2, and on k bits it's 2 to the k. So if you tell the value of the function on uh, all possible inputs, which is all 0 inputs all the way to 1 to all 1 inputs, how many are going to be there? It's going to be indexed from 1 to 2 to the k. And if you tell me the value on each possible input, that completely describes a Boolean function. So any Boolean function on k bits can be written explicitly as a truth table on 2 to the k bits. So here is an explicit, I did not formally define what explicit is, but this seems natural, right? I mean, I am telling you what the function is on every possible input. Explicit representation of any h takes 2 to the k bits. So this is another simple fact. Yeah. So how are we going to get p not equal to NC1 from this? So I guess I have about like 8 minutes left. So I'm going to try and conclude with this. So this is the idea. So as we saw earlier, what we're going to do is we're going to compose h with itself, and we're going to compose it some n number of times. Sorry. So this means h is composed with h itself n times. So, and what's the depth is what's if KRW conjecture is true, what is the depth of this function? It's going to be depth of h times n, right? And we are going to use this function. We know that there are indeed Boolean functions whose depth is something like k over log k. So let me plug that in so that we get that the depth of this new function is nk over log k. So there are 2 challenges. One challenge is that this h has to be explicitly given, because we only know that there exists such a function. So we have to somehow make this h composed n into an explicit function. So goal number 1, turn this into an explicit function. Goal number 2 is figure out best n, so the depth that we get is nk over log k. So depth of h compose h of n is nk over log k. And what's the input size of h? Input size of h composed n is k to the n. So we want to find a good trade-off between these 2 values decided by n. So we will decide how many times we want to compose to get the best trade-off, to get the maximum possible depth before blowing up the input into something too large. Okay, so I guess there are more people. Okay, I know. If you're joining at this moment, it might not be clear what we are talking about, but I'm gonna record. I'm recording every lecture, and it will be uploaded to YouTube within a day, or yeah, if nothing bad happens, it will be uploaded within a day. So this is our goal. So we want to use, like, we want to first turn the description of h composed with n itself n times an explicit description, and we want to find out this trade-off. So here is this idea due to like Andreev. So what we're going to do is, like, we're going to build a new function. Let me call it, I don't know, I'm out of good names. Like, let me call it capital H for lack of a better name. So this function is going to take two parts. So let me call this input x. So this x is going to be n bits, and it's going to have this other part which is y, which is also n bits. So it's a function on 2n bits. Okay, so here is how to interpret this function. So this first part is thought of as a truth table of a function h on log n bits. So if you recall, we had this basic fact written earlier. If you have a function on log n bits, how many possible inputs are there? 2 to the log n inputs, and 2 to the log n is exactly n, so there are n possible inputs. So x tells you the value of the function on all possible Boolean inputs. So this is an explicit representation of h. See, this is what we wanted to get to, right? We only knew that there is some good function with very good depth lower bounds, but we don't know what that truth table is going to be. But we know that there is some truth table on n bits where, so if you remember, fact 1 told us that there exists h, so equivalently there exists this input x in 0 1 to the n. So there's some Boolean value that you can assign to x such that the corresponding truth table, the function whose truth table is x, that h has depth complexity k over log k. So the first part of the input gives you this function h on k bits. And but now how do we compute the output of this Andreev function? Let me call it capital A. Okay, so how are we going to compute a on x comma y? So this is what we're going to do. So let me just recall, these are both n bit inputs. So h is thought of as a Boolean function. Let me denote it by hx. So based on the value of x, it will be a different Boolean function. So it's on log n bits to 1 bit. So this tells you a Boolean function, log n bits 1 bit. And y is y1, y2, let's say y log n, so on and so forth, y n minus log n, maybe plus 1, yn. So y is an extra n bits of input, right? So we divide, so what we do is like we divide y into log n bit chunks. Okay, so now this is primed to be an input for the function hx. Remember, hx is a function on exactly log n bits. So you divide the input into log n bit chunks and apply hx on each one of them. So what do you get? You get again Boolean inputs, but how many are there now? So they're going to be, here you had n bits, right? Sorry, this had n bits, but now here you only have n over log n bits of input, right? But we want a to be a Boolean function, so we want just single bit of output. So I'm running out of time here. Can I take 5 more minutes? If anyone has to leave, they're free to, and maybe watch the remaining on the YouTube. But yeah, I'll need 5 more minutes to conclude. So basically, what do we do next? We again do the same thing. We bunch these intermediate input into log n bit chunks, and then again apply. What do we apply? We have hx, apply it again. So remember, we had this idea that we should have this hard function and compose it with itself. So what happens now? How many bits of input output do we have at this layer? Any guesses? So you had n over log n bits, you divided into log n bits chunks each. So how many should be left? How many buckets are there? N over log square n. Yeah. And what do we do next? Keep going until we get 1 bit of output. So again, bunch them into like log n bit chunks, apply hx again and again. So but then how many times do we have to apply hx? So we first applied hx to n bits, and then we got something like n over log n bits, and then we went again, applied hx to get n over log square n bits. So it's not one application of h, but like many applications of h all in parallel, right? So when do we get one bit of output? So at the jth level, so at the jth level, how many bits would we have? We would have n over log n whole to the power j. So every time we are dividing by j, right? We are dividing by log n. So, and we want this to be like one bit of, so at some point we want this to be like exactly one bit, and that's going to be the output of the Andreev function. So what is that going to be? So if we try to solve for this, so we want to find out j. So find j such that n over log n whole to the j is 1, which is equivalent to saying that log n to the j is n. Apply logarithm, you would get that j is log n over log n. Yeah, right. So in fact, so if you have, so what does it tell you? So if you have the Andreev function on x comma y, this is equivalent to, you apply, take this function hx, which is on log n bits, and you compose it with itself these many times. How many times? Log n over log n times. So you're taking this function and composing it with itself these many times, and then you have, and what's the input to that? It's y. Okay, so now here's what we're going to do. We knew, we had this fact from earlier that there's some function h on log n bits whose depth is something like this. It's very high. Okay, so what is that depth is going to be? So we know there exists h on log n bits. So this, any function on log n bits is equivalent to a truth table of h, which you can think of it as a assignment to x, a 0 1 assignment to x. So there is equivalently, there exists some x such that this function, if you think about this function h of x, the depth of h of x is k over log k, but k here is log n, so that's like log n over log n. So we know that there is some setting of these inputs x such that the resulting function d hx has very high depth. So it's not explicit, we don't know how to set this, but magically there is this setting. And now so this is claim that I make, that depth of this Andreev function is at least the depth of this Andreev function, where I fix this x to be this large complexity function, the truth table of this large complexity function hx, and leave the remaining as it is. So what I'm saying is that if you have a function, and if I restrict some parts of the input, the depth complexity cannot go up. This is a easy exercise. Maybe I'll give it as an exercise, but if you believe me on this fact, I mean, you think about it, right? You have a circuit, then you fix some inputs, some constants, it can only simplify things. So depth is going to be at least this much, and we know that this, the Andreev function on some input x comma y is this function hx composed with itself n times applied to y, right? So this is equal to depth of hx composed with itself n times, and by KRW conjecture, what is this is equal to n times depth of h of x, and we plug in an x where this is log n over log. So maybe this n was a bad idea, so I should have called it something else. So the number of times I composed, I called it j. So the number of times I composed, let's call it, yeah. So this is j times, it's j times dh of x. So it's j times log n over log n. And we figured out that j, value of j is log n over log n as well, right? So what is this final value? So depth of this function is at least log n over log n times log n over log n. And what's its input size? It's exactly 2n, right? It's not n, there's x and y, but okay, for this one I fixed x, there's only n bits, but it's linear. It's theta of n. So the depth of this new function that we got is log square n over log n, and this n is the input length of the function. So this tells you that this function cannot be computed in logarithmic depth formulas. It says something more. It says that even if you go to log square n, this is hard, but yeah, I mean, it's slightly smaller than log square n, this is hard, but definitely you cannot do this in log n depth. So if the conjecture is true, it implies that this function, the Andreev function, has very high depth complexity. So you might be still wondering, why is this function explicit? So it seemed like we plugged in this value of x, which was like, I don't know, we only knew the existence of some x where h value is high. So it seemed like it's not very explicit, but it is. So we use this intermediate fact that, so Andreev function with some of its bits fixed has, its depth cannot decrease. So depth of the Andreev function is at least the depth of the Andreev function with some of its bits fixed. So we get that depth of the Andreev function, which is very super explicit, right? It tells you, given x and y, this is how you should treat the input to get the output. It's very explicit. This explicit function has depth at least log square n over log n. So, and this is sort of the optimal trade-off between the size k of the input function h and the number of times you compose to get a good depth lower bound. Okay, so I think, yeah, that's all for today. So if you have any doubts about this last part, please ask me. I think I went over it quite fast. Or anything else, if you have any questions, please let me know. Otherwise, we're done. Yeah, so just oh, okay, just one more thing before we conclude. I just wanted to say that, so what is this approximate equality? So I used equality to prove the lower bound, but even if you replace this equality with something like, okay, let there be a constant epsilon such that depth of f compose g is not necessarily depth of f plus depth of g, but it's depth of f times epsilon times depth of g. So epsilon, think of it as like half. So maybe depth doesn't add up, but it's like depth of f plus half the depth of g. This still gives p versus n7. The proof that we saw would still give you a good lower bound, and you can similarly like define it to be epsilon depth of f times depth of g, or you can make a mix of epsilon depth of f plus gamma depth of g, but then you need some kind of relation between epsilon and gamma. But the main point is there are many ways to define this approximate inequality, so that this proof that I showed you, which said that if the conjecture is true, p is different from NC1, still holds, and it's still true. Yeah. So that's all for today.